Well, like everyone else, I'd like to thank the organisers for having me here to this gorgeous place and, have these nice beach walks and meet all these interesting people. And for me, it's a little bit of a new exposure to real data. I mean, it's sort of trying to learn how to sort of understand plots and then see people who actually calculate things that relate to it. And I feel slightly embarrassed here, maybe a little bit of an interloper, that I will have no formula for momentum kicks or angular momentum kicks or even a waveform. So I think I'm past the program that's a little bit more of the out there aspects of new or unusual methods for computing amplitudes. And so what I'm going to talk about today are the computation of amplitudes on non-trivial backgrounds. So this is meant to be backgrounds that are not flat. And one of the reasons why you might want to do this is so that you can encode fully nonlinear effects that are exact to all orders. At least some of your calculation is, so you'll have maybe some perturbative calculation on a background, but that background would already be non-flat. But to do this is quite a challenge. I mean, one of the first things, in fact, if you're interested in scattering amplitudes, is what are you going to scatter? So you've got to think about sort of what sort of waves that you're interested in. And of course, everyone uses momentum eigenstates. And but what is a momentum eigenstate on a curved background? You don't really know. You're then going to need to so you've got to solve the field equations and decide what a momentum eigenstate is. You've got to construct propagators on the background, and then you've got to do space-time perturbation theory, which will involve, for example, for n-3 particles, n particles, you'll have n-3 full space-time integrals. So it's a lot of work. And as a consequence, actually not an awful lot has been done. And by and large, I think 3 or maybe 4 points is the limit in spacetimes that have got some sort of genericity, some functional degrees of freedom in their curvature. If you just think about spacetimes that only have one parameter in their curvature, like ADS or de Sitter, or the BMN sort of plane wave, then people have gone up a bit higher. But even for BMN, I think they only went up to 3 or 4 points. So this is not really a field that's wide open yet, but I think it has promise. So my defense in not giving you any waveforms or whatever is that this technology is rather nascent. But what I can do is give you all multiplicity graviton formulae on backgrounds with full functional degrees of freedom for the self-duality condition. So these are, they will depend on all 4 variables. And in some sense, the self-duality condition is giving you half the phase space of general relativity. So how do we get around some of the issues? Well, we're going to think about sort of asymptotically flat spacetimes and ones in which you have both a scri plus and a scri minus. And there's some history here. Ted Newman set up this framework for studying these spacetimes by thinking about the way in which the light cone of a point X intersects null infinity, and he introduced the concept of a good cut. And the good cut was one that was asymptotically shear-free as it hits infinity, but it had to be complex in order to kill the shear. The shear is a complex parameter on the cut, and so his cut was actually sitting in the complexification of scri. But he could construct a 4-dimensional family of them. And what this 4-dimensional family was it turns out that it was a spacetime that satisfied the Einstein vacuum equations, but it was complex and its Baal tensor was self-dual. It was in some sense circularly polarized. So this was a bit of a miss, but this H-space encodes the self-dual gravitational data. It is, so to speak, that half of the spacetime that you first thought of. This led to a big breakthrough for Roger Penrose. It led to his nonlinear graviton construction. He reformulated this in twistor space. He constructed a twistor space at null infinity, and he reformulated his construction as a kind of an integral system. So this is before integrability was really, well, integrability was rising at this stage. This is the 1970s. What I'm going to do in this talk is to use this completely integrable subsector of Einstein's equations to try and gear up to give you a perturbation theory around that completely integrable subsector. So the integrability will enable us to actually do calculations that are very explicit and will take you a surprisingly long way. So the hope can be, you see, so Ted Newman missed in the original space-time by constructing this H-space, but maybe we can use amplitudes to perturb away from that H-space to build up the data of the original space-time. So that's kind of, roughly speaking, the underpinning idea for this talk. Okay, actually, I've only got half an hour, and I should probably. Well, any questions? Yeah, please.
Is this H-space very general, or like you just call it H-space?
So H-space is a four-dimensional space-time that's complex. So it's four complex dimensional, and it has a metric that satisfies the Einstein vacuum equations, but it only has half the Weil tensor of the original space-time. Its data agrees with half the data at Scry. It agrees with the self-dual half, but it misses out the anti-self-dual half. Okay, it's difficult to draw a picture of that. Okay, so that's where the techniques are going to come from, is this twistor theory, and I'll explain some of that a bit later. What can we do with it? Well, just to focus ideas, I'll focus on one scattering amplitude that I want to extend to a curved background, to one of these self-dual curved backgrounds. So the kind of most famous sort of multi-endpoint amplitude is this MHV amplitude, where you have two negativity particles and the rest are all positive. And so, as is common, we can use the spinor helicity notation. So if you've got these n momenta, these are all null. And if you use spinors, you can rearrange these null momenta as 2x2 matrices. And the 2x2 matrices, if it's null, turn out to factorize. They have rank 1. And then we can, these are two component spinors now, these kappas. So there's two pairs, there's a pair of spinors for each particle. And in fact, the scaling of the spinor contains the polarization data. So we can use these spinor contractions as the Lorentz invariants that we'll need to build an amplitude. So 10 years ago, Andrew Hodges found a beautiful formula for the MHV amplitude. And to do this, he defined this n by n matrix, which is made out of the spinor contractions of each type of the momenta of the particles that are being scattered. And I'm doing this a little bit schematically just to unclutter the formulae. The amplitude, the tree-level amplitude, was given by this expression. It's a reduced determinant of this matrix. So reduced just means you knock out 3 of the rows and columns. And you had to divide by some factor to get the scalings right. And it was actually observed very soon after Andrew's formula that this actually related to some older work as maybe David, and anyway, Perelstein, Rosolsky, I can't remember, well, anyway. And this older form of Zvi Bern and friends expressed the gravity MHV amplitude as a sum over tree diagrams. So Andrew's formula sort of related to this. So you imagine you have tree diagrams, you've got sort of n minus 2 vertices, and you allow all sorts of trees, and you sum over them using the matrix tree theorem. And this matrix, this reduced determinant is precisely what the matrix tree theorem tells you is the sum of the, sorry, that was a terrible diagram, sum over trees. So one of the things I hope to answer in this talk then is, so tree diagrams, you start to think, well, there's some theory there. Maybe there's some action, and maybe we can actually see some substructure in gravity that's unexpected. And so that's one of the things I hope to tell you about in this talk. And in fact, what we'll see is that this formula here is a tree correlator. And so once you know that, you can then sort of, so that's a cute thing to know. It explains this old result of Byrne, Dixon and friends. And, but it gives you the power to actually extend it to give you a formula that can live on a more general background. So, okay, so what do you expect to happen on the background? Well, first of all, that one of the nice things about self-dual backgrounds is that they admit covariantly constant undotted spinors. So these kappas for your particles survive as constants. And furthermore, you can sort of prepare, because we're talking about asymptotically flat spacetimes, we can prepare our momentum eigenstates as infinity. And the fact that it's integrable means that it doesn't matter which infinity you use. You can use H plus or H minus. Because it's an integral system, there's no scattering. I should say that when you do scattering on an ordinary plane wave, one that's not self-dual, that would not be the case. Your plane waves at Scri minus would not evolve through to anything that looked like a plane wave at Scri plus. So the undotted spinors are not constants, but we can dress them. And so we can these, in particular, these spinor contractions can be dressed in such a way that they make sense in the formula, but they become x-dependent on spacetime. And so we end up being able to define an x-dependent version of this Hodges matrix. But we also expect there to be interactions with the background. So graviton's going to hit the background, and then it's going to scatter off a bit. And then that scattered particle can then scatter again off the background. So these are sort of tails. And so you can have T interactions with the background, but the T is bounded by the number of particles. So T is smaller than n minus 2. And what we see, though, is that with the benefits of the theory that we can develop, we still need to look at tree diagrams, but they now have to take into account all of these vertices that are formed by the background. And so we can do the same sort of trick before to write the amplitude in terms of some generating determinant, but now with a larger determinant, which is now sort of slightly smaller than sort of 2n by 2n matrix. So in some sense, this is something that's sort of computable in sort of very finite terms, albeit for large n, of course, it's going to get messy. And you have to sum over all the possible numbers of tail terms and so on, but by and large, we get a formula that's pretty much as tractable as the original MHV formula. Okay, so I want to tell you about how this comes about and to make that schematic formula a little bit more concrete. Sorry, well, yeah, maybe I can sort of leave questions until a little bit later. So what I want to do is to explain how, at least in the case of the MHV amplitude, we can actually derive this from the space-time action. So we're used to the idea that an amplitude is the evaluation of the action of a perturbative solution. And so one of the first things that we do then is, at least in the MHV case, we can actually reformulate the Einstein-Hilbert action on a self-dual background to give you something sort of rather neat and unexpected. And this then lifts to the twistor space, and it can be related to a sigma model, a sort of a chiral sigma model inside that twistor space. And then you can do the computation. There are various things that one could do with that afterwards, but I almost certainly won't have time. So the first statement then is first of all, what is an MHV generating functional? Well, what you imagine is that you take the ordinary Einstein-Hilbert action and you perturb it twice in the direction of two linear fields, H1 minus and H2 minus. So this is going to be a pair of anti-self-dual particles. And then you evaluate that on the self-dual background G+. So that's what I mean by a generating functional. And furthermore, we're going to actually take these HI1 minus and we'll take these to be plane waves at null infinity. So we'll prepare them in the far past, so to speak, so that they have this momenta. And what this allows you to do, actually, is to introduce coordinates on the spacetime that are adapted to the two particles. So we can organize the coordinates in this 2x2 matrix as before, and we can sort of use one of the momentum spinners to give you one pair of coordinates and the other one to give you another pair. So we have an x after dot and an x tilde after dot. And with that, it's an old result from the 1970s that a general self-dual metric can be given in terms of a simple scalar, capital omega. And this capital omega satisfies what's known as the Mondrian-Payer equation. And that's what's left of the self-dual Einstein equations in this self-dual context. So one of the things that we do then is we can start from the standard Einstein-Hilbert action, which is just the scalar integral of the scalar curvature, and we can sort of take the second perturbation with two negativistic gravitons. We can do a couple of integrations by part, and lo and behold, we find that this Pabansky scalar is a generating function for the amplitude. So by generating function, what I mean is then that if you construct a G plus perturbatively, this would, from say another n-2 positivistic gravitons, then this would then give you the full MHV amplitude. Okay, any questions? Okay, so now this is where I get to pistorial. So the point is here that expanding this would be tough. You've got to sort of expand your omega in terms of some plane waves. You've got to expand this equation, and you get back into the world of ordinary space-time perturbation theory. But we have this twistor construction, and so here is what twistor space is. So twistor space is a four-dimensional complex space. We have four coordinates on it, a spinner, and it's one spinner of each type, lambda alpha and mu alpha dot. But we often think of it projectively. So the overall scaling is something that we can quotient by. So in terms of the true degrees of freedom, we'll try and keep things homogeneous in these coordinates. And so there's really only functions of three variables there. And in some sense, it's a space of true degrees of freedom of the solutions to field equations. So typically, one can solve wave equations by performing integrals of functions on twistor space. We're going to need some extra structure here. We have this Poisson bracket. So the mu coordinates are specially geared so that we have a Poisson bracket on pairs of functions on twistor space. And so twistor space itself is a conformally invariant space. It's conformally related to space-time. It's in fact a spinner for the conformal group. But when you introduce this Poisson bracket, you break conformal invariance, and that's necessary for gravity. The gravity data is given by a 0-1 form on this space of homogeneity degree 2. And this can be constructed directly from the asymptotic data. So this is what would have happened in Ted Newman's original construction, that sigma naught is the asymptotic shear. At scry, it's the half the asymptotic data for the self-dual part of the field. And this H would just be simply a U integral at the Bondi retarded time of sigma naught. But you can actually do, the twistor space gives you a more flexible framework. So you can have functions, if you wanted to do a black hole, a self-dual black hole, you could think of other functions which weren't obtained in this way. And then the idea is that this asymptotic data at null infinity is deforming the complex structure on twistor space. So that you've got a d-bar operator that tells you when a function is holomorphic, function of the lambdas and mu's, and it's obtained thinking of this H here as a Hamiltonian for that Poisson structure. Okay, so there's a statement of what Penrose's twistor space looks like. For people who haven't seen it before, I'm sure it's kind of not completely easy to absorb after a whole week of. Okay, well, I'll carry on. I mean, if you. Okay, so that's meant to encode an entire space-time. So how do you reconstruct a space-time from the twistor space? We've got the twistor space, it's got a deformed d-bar operator on it, a deformed complex structure, and that's meant to, so we can reconstruct the space-time via a kind of an integral systems trick by looking at an auxiliary problem. And the auxiliary problem is to look for holomorphic curves inside the twistor space. This is meant to be a cartoon of what twistor space is. And what we're going to do is we're going to look for holomorphic curves, which are meant to be these black lines here. And these would be solutions to a differential equation. So at degree 1, I'm writing these out in a slightly odd way. So the lambda alpha, I'm writing in terms of sigma. So I'm really thinking of this is only really important when you get to higher MHV degree, which I probably won't get to. But you write your curve in this way, which makes it look singular. But what I'm trying to do here is I'm trying to pin down a couple of points on the curve by projectively, this would be the same as just saying that mu is equal to x naught at sigma naught equals 0 or x1 at sigma 1 equals 0. And but the main thing is that this thing is meant to satisfy the deformed d-bar equations. And because this is just a graph of mu being a function of lambda, essentially, these sigmas are basically the same as lambda, you can express it quite simply in this way. So we end up with a differential equation, and it has, you can prove that it has a 4-parameter family of solutions, and that's going to be this space-time. And then you say that 2 points in the space-time are null connected if the corresponding curves in 3 space intersect, if they touch each other. So that's how the construction works. And Roger Penrose then proves that it's Ricci flat and self-dual. What I'm going to need from this is that equation here, this d-bar equation for the holomorphic curves, has an action. So we call this a sigma model, but it's really chiral. It's a d-bar of m equals something. And the sigma model has this very simple action. And I've set things up so that all the weights are correct in this form. And what we then prove is that this action computes the Perbansky scalar that I was talking about on the previous slide. And if you remember from the previous slide, if we want to compute the MHV generating functional, then we needed to have some way of arriving at this Perbansky scalar. So the Perbansky scalar then is the onshell action for the holomorphic curves in twistor space. And then if you can evaluate this onshell action, then this is what the metric is, the self-dual metric. So this gives us then this formula then for the generating function for MHV amplitudes. Okay. Any questions? I've got 6 minutes left, have I? Okay. Okay, so now what we have then is that this generating function is given by an action, by an onshell action. And so we know how to compute onshell actions perturbatively now, because we can just use standard tree-level Feynman rules. I mean, it's slightly, maybe slightly different from usual. So what we're going to do is we're going to say H is a sum of the from 3 up to n of momentum eigenstates. You have to know that momentum eigenstates in twistor space are going to be given by a formula like this. We know this from the days of the twistor string, I guess. And then if you want to compute the action here, the onshell action, then you're basically just saying that this H is equal to that sum of the HIs, and you bring them down in the kind of tree-level path integral, and you get a correlation function of these, what I would call here vertex operators, but they're very simple. They're just integrals of these H's over the Riemann sphere. They have the right weight. They had weight 2, but it was expressed in this in negative homogeneity language that I had before. And the action is such that we had the square bracket as being the kinetic term in the action. And so what you discover then is that this square bracket just pulls down the tilde momenta, and the propagators then, or the contractions that you get in this correlator, are precisely the propagators of the tree diagrams that Byrne and friends, Zvi and friends, found sort of a quarter of a century ago. And so it yields their tree diagram formalism, and it yields the matrix tree theorem, then it yields the reduced determinant that Andrew Hodges discovered. Okay, so that somehow gives an explanation then that the Einstein-Hilbert action, at least in this approximation, has this substructure of this onshell sigma model, chiral sigma model in twistor space that defines the holomorphic curves that we build the space-time. Okay, any questions? 3 minutes left, sorry. Okay, I'll try and be fast. Well, you can do this at a higher degree, and you get the rest of the S matrix. That's those 2 slides. Yeah, so that wasn't just MHV is the point, so we can extend it. And I'll fast forward now to the perturbations on the self-dual background. So if you want to then have a self-dual background, we're now just going to do a perturbation around an H0. And so now this is a relatively standard thing to do, because what you do is you then look at the quadratic approximation, and we use that to build your propagators. And so first of all, we need to actually solve everything on that background, but this is something you can do with integral systems technology in good situations for many examples. And so we have to solve this equation, but we can do that for some nice examples. And we can write down this, the quadratic perturbation and find the propagators for this. And we can also write down a bunch of vertices. And then if you want a correlator of these vertex operators, then we on this background, we can first of all see that the quadratic approximation to the action gives rise to a decoration. It dresses the propagator that we had before with some matrices that are easily computed from the original solution. And that's what's going to give us these dressed dotted spinner contractions here on this background. But we can also have T of these vertices, the T tails, so to speak, or vertices that generate tails, that are now coming from the background. And so with that, we can compute a correlation function of the n-2 self-dual gravitons and all of these vertices. And we can compute that as a sum of trees, so we can again use the matrix tree theorem. And all of these are explicitly yeah, so this, as I said, you have the dress contractions, and these other terms are propagators between the these vertices and the sort of background vertices and so on. And so I'll leave it to your imagination. Once you've got a framework like that, you can piece it together and you can write it all in terms of a generating function with the step prime h, and you can sum over the different tail contributions and stuff. So there's a plenty of self-dual backgrounds which have good functional degrees of freedom on which we can make all of these ingredients explicit. So this is for the radiative given Hawking models, self-dual black holes, and so on. We can do this quite explicitly. 1 minute left, okay. At endpoints, you expect n-2 space-time integrals. Here, there's just one. And in the case of a plane wave, I mean, 1 d4x, but on a plane wave, all of these integrals but one actually localize. Okay, so conclusion. Yeah, so what I've seen is then that gravity tree amplitudes can be generated by the onshell action of sigma models for curves in twistor space. The Carroll sigma model gives you the exact value of the Einstein-Hilbert action at MHV, but at higher MHV degree, we don't quite know what we're doing. But at higher MHV, we are looking at a higher degree map. And we have to insert k particles in particles into the world sheet instead of just one. We can this works much the same way for Yang-Mills for non-zero scalar curvature, we can include self-dual black holes in the background. One of the things that I realize I need to do in order to make contact with what you guys have all been doing is to sort of think harder about how can we extend to general word lines. So that's something that we need to do. And there's a whole story about celestial holography here. That Poisson bracket is intimately related to this LW1 plus infinity. But I think I better just say thank you and finish. Thank you.
Thank you, Lionel. We have questions.
Yeah, thanks for this beautiful talk, Lionel. I was wondering, since in flat space-time, I can rewrite the Hodges determinant in terms of a KLT formula for Park-Taylor factors of angular brackets. Is there any echo of that in curved space-time? And if so, is it advisable to try it, to use it?
That's a nice question, actually. I mean, one of the things that's remarkable in this is the simplicity of these background vertices. So these here are the background vertices. I mean, there's some derivatives of the asymptotic shear, but they come out in a very uniform way. So it'd be tempting to think that they would participate somehow in the sorry. So these are the propagators between the kind of the positive graviton vertices and the background vertices that you get from expanding the background around. Yeah, so it is tempting to think. Yeah, I don't know, but that's a very nice question. Thank you. It'd be tempting to think you could say something about double copy here. One of the things that's weird is that the twistor description hides the double copy into the geometry of the twistor space. The CHY description, you would have two such determinants. You could just have CHY has two Pfaffians. The Pfaffian's equal to the determinant, and CHY would have two of them, and that's your double copy. One of them in the twistor descriptions is absorbed into the geometry, so it actually gives a geometric realization of one of the copies. And I guess I was just discussing with Sylvia earlier as to how we can try and understand that as something to do with kinematic algebras. It's always been tempting to think of that, but it's never quite emerged.
Yeah, thanks for the helpful reply.
Thank you.
If there was another question.
So your self-dual black holes could be something like a Kirchhoff node, not a self-dual point?
Yes, so you can't tell the difference between Schwarzschild or tau of nut in the self-dual sector. You can't tell the difference. If you're a complex, you can't tell the difference between Kerr and Schwarzschild. I mean, I guess Schwarzschild has to be complex because you're taking the self-dual part plus IA and the anti-self-dual part minus IA. So somehow, anyway, but you could get the analytic structure of Kerr and Schwarzschild there, but just a self-dual half.
Yeah, yeah. But I can then scatter, you know, so I could get the analog of the Compton amplitude with specific helicities directly from these formulae.
Yes, yes. I slightly worry in my last question that this isn't enough to do sort of, because I mean you would like to have a general word line or a proper real black hole, whereas of course this will be a self-dual one. So I don't know to what extent that does damage or not.
I mean the nut charge is just going to be an overall phase, and you know, I guess we know how the spin. Well, I mean the spin is a translation in this picture, right? Yes,
that's right. That's right. So. Yeah, so I haven't really experimented with it. I don't know how much it buys you, you know, or how much you miss is, I guess, the real.
Yeah, but I guess the point. Yeah, so it's just, you know, so there's some specific helicities of the outgoing gravitons I can pull off from this.
Right. So, well, we can do gravitons of both helicities if they're self-dual. They're easy, and if they're anti-self-dual, they're hard because you have to do. There's an extra three-dimensional integral for each anti-self-dual graviton, whereas the self-dual ones are in some sense local. So it's definitely lopsided. It's much harder to do to scatter negative helicity gravitons on this background.
I mean, is there any obvious reason why you can't just get the whole amplitude for, you know, let's say something like Kerr-Taub nut by averaging essentially the self-dual and the anti-self-dual have? Well,
I think that was my image. So one of the the image was in some sense that you know, you have your self-dual black hole and then you maybe fill in the anti-self-dual part with perturbations. I mean, it's still better than space-time perturbation theory, even when you've got lots of. I don't know if I've got enough detail on the. I skated over the sigma model at higher MHV degree, but you only have 3 integrals per negative helicity particle, so I think it is slightly better than space-time. But maybe it's starting to get to a point where it's getting laborious.
Okay. Yeah. Thanks.
Thanks for a nice talk, Lionel. So you described this generating function just as onshell action. And for gravity amplitudes, if we focus on MHV, to show that this formula is permutation invariant, this relies on the fact that there's these bonus relations for gravity amplitudes, this kind of sum over residues that kind of give you a relation between different ways of writing. Do you know if from this perspective, does this give any new light on these bonus relations? Because this was related always to the good large D behavior of gravity amplitudes, which is a mystery in a sense. So I was wondering if this perspective tells you something about that.
Well, so that question is also a question about finding an n=8 formulation. So to see the full symmetries of the gravity amplitude, you only see it with maximal supersymmetry. And yeah, I think at this stage, actually, I just have to confess that I mean, I've thought about it a bit, but it's not as immediate as. So somehow for the gravity twistor string, you could just do it. And in fact, you know, David Skinner will tell you that it was only critical. You know, the anomalies would only vanish at n=8. This is very much a tree level thing. I'm sure it's sort of full of anomalies when you try and try to quantize it. But the yeah, the way in which the you see, what you have to do is you have to try and sort of permute the H. Well, it's hard. I haven't managed to do it. Is the short answer to see how to make it n=8 supersymmetric. And that's definitely a challenge. I think you would definitely learn something even if you weren't interested in supersymmetry per se. You'd learn, as you say, you learn about the analytic structure of the amplitudes and so on.
Thanks.
So I guess there I've exposed the fact you've got 3 extra integrals per particle. And there's also an extra fudge factor, so another reduced determinant in the higher MHV degree version.
Any final questions? Okay, I think that's it. So let's thank Lionel again and all our speakers of the afternoon.
Thank you.